graph norms for complex value please.
All right, thanks for coming. It's my great pleasure to be here to give a talk in front of non-virtual audiences and virtual audiences too, hopefully. Anyway, I'm going to talk about graph norms for complex valued function, and this is joint work with Alexander Sidorenko. Okay, let me start by defining graph homomorphisms. So graph homomorphisms are vertex maps from a graph H to another graph G that preserves adjacency, which means whenever I have an edge here, the image of the edge is again an edge. Okay, and graph homomorphism density is a number that encodes a randomly chosen vertex map is a homomorphism. So it's just a number of homomorphisms from H to G divided by the number of vertex maps. I can rephrase this a little bit by taking probability into account, which means this is a probability that random, by random I mean uniform random, random phi chosen from all the vertex maps from H to G is a homomorphism. And yeah, I can rephrase further by replacing my probability by an expectation. So, okay, then this event, the indicator of this event is nothing but this. So whenever my edge UV is in H, the indicator that a randomly chosen vertex, so I'm going to choose each vertex in G, so these are G vertices, so these are in G, and I'm choosing these independently at random for every vertex U, in H. Okay, and then these two images, the randomly chosen images U and V, are adjacent in G. Okay, let me just rephrase further by just saying, replacing this indicator by this. So here gxy means the indicator function for edges. Okay, if I go this further, then it's quite natural to replace my g by a function. So let me just say, and I can even replace my expectation by an integral, and just say that this is the quantity I'm gonna look at. Okay, so I'm gonna integrate all these with these. For f from 0, 1 square to r. Well, one may assume that f is symmetric or not. It depends on the setting you're looking at. Okay, this is a natural generalization of the graph homomorphism density for symmetric functions on a unit square or non-symmetric functions on a unit square. For non-symmetric functions, you need some orientation, so you might need H being bipartite, but let me just postpone that technicality for now. Okay, then the question by Lovas asks the following. So let me say my H norm of the function f is my H density to the number of 1 over the number of edges in H. Okay, because there are exactly, so the number of functions here is exactly the number of edges in H. So like we do for LPs, we normalize that number on the exponent to have the homogeneity. Yeah, when we put some constant here. So the question is, when is this quantity a norm on the vector space of like 2 variable symmetric functions, or just 2 variable functions? Okay, this is a question, and so you might wonder why this question is an interesting one, and why is it worth studying?
It just reminds us what norm would be.
Okay, yeah. So this is a norm. If so, this is the definition. First, this is 0 if and only if f is 0. So in this case, I should put almost everywhere here. And second, some c times f is so the constant here pops out basically with absolute value. Yeah, and to that end, I normalize this term. And third, the triangle inequality. Yeah. So yeah, these are quite easy to check. So the entire difficulty lies on the third, the triangle inequality. Okay, so this is a definition of norms. Sorry? Sorry. That was a typo. Yeah. Thanks. Yeah, that was a typo. Yeah. Okay. So this is a basic setting, and yeah, I'm going to explain why this is an interesting problem. So first, it's a generalization of well-known concept, so-called Gowers norms. Gowers norms. So this goes back to these beautiful results by Chong, Graham, and Wilson, and by Thomason on about quasi-randomness of graphs. But let me just explain in more kind of Gowers type context. Okay, so Gowers norms were originally defined for function f's from some group, say Zn or Fp to the n. So I'm gonna put some group here. So additive group or abelian group. And it's defined as follows. So there are higher Gowers norms, but let me just give you one example of them. So Gowers U2 norms are defined by f of x plus y, x plus y prime, x prime plus y, f x prime plus y prime. And you take the 1/4 root of the quantity. Yeah. So this is the definition of Gowers U2 norms, and there are higher Gowers norms like UK norms. And this has a graph theoretic analog which is the full cycle norm. So if I do this for a full cycle, then what I'll get is let me just exchange. Okay. Yeah, so what I'll get is this. So this is a special case of the full cycle norm for Cayley graphs. Basically. Yeah, again, I forgot to write these down. Ah, okay. Thanks. Yeah, so these played on these norms, these Gowers norms played a very important role in additive combinatorics, especially his new proof of Symmetries theorem by using Fourier analysis. And yeah, this is a really central, like, key tool in many theorems in additive combinatorics and the theory of quasi-randomness. And one interesting fact is that when we consider the Fourier transform of these functions, so I'm not going to define what Fourier transform means, but there's a standard way of doing Fourier transform for this, okay? Yeah, so then this Gowers norm for Gowers U2 norm exactly corresponds to with the Fourier transform, the fourth norm of the Fourier transform, which gives a very nice tool. So, but the thing is, when you do this Fourier transform for functions, even defined, even for real valued functions, if you take Fourier transform, then it's quite likely that you get a complex valued function. Because you no, the 4 norm is the L4 norm itself. Yeah, it's different. Yes. Yeah. So the 4 norm means this. Yeah, but the thing is, even if I take a real valued function, I'll get complex valued function here. So to make this inverse Fourier transform complete, it's quite natural to consider the complex valued functions for this definition. So to extend this definition for complex valued functions, one should do this. So for complex valued functions, one should put conjugates over here. So this is how you define a norm for Gowers U2 norm for complex valued functions. And the same holds for the full cycles too. So what you can do is basically either you put a conjugate on your function or just leave it as it is. So to define, okay, I'm not that tall. Okay. So to define these graph norms for complex valued functions, you should pair your graph H with a 2H coloring alpha that determines where I assign conjugates or not. Okay, so here alpha is the 2H coloring. And then what I'm going to do is to define this corresponding density, which is this. Yeah, so if alpha is 0, then this is 0, this is 1. So I'm going to take the conjugate. And if alpha is 1, then this is 1. So I'm taking the non-conjugate term. So this is a definition for this pair, the color graph, the homomorphism density of color graph. And then again, this is just the density to the 1 over the number of edges in H. Yeah. For example, if you look at this full cycle here, then my coloring is, for the full cycle, my coloring is just the alternating coloring of the full cycle. Yeah. So here, this vertex corresponds to X and X prime, Y prime. Is that right? Or the other way around? X. Yeah. Yeah, so this is how you define the homomorphism density for complex valued functions and the corresponding norms. Okay, then here's another question, which is a natural generalization of Gowers norms. This is a question by Hatami saying when is this a norm on the space of complex valued functions. So yeah, let me say that if this is a norm, then my H is real norming. And if this is a norm, then my H alpha, the two-edge color graph H alpha, is complex norming. And furthermore, if there's a two-edge coloring that makes the color graph H alpha complex norming, then I would simply say that my graph H is complex norming. If exists alpha, such that H alpha is norming. Okay, so far so good. So, well, so these questions are interesting by itself because these are generalizations of Gowers norms, which is a important concept. But it also has applications to Sidorenko's conjecture, which is one of the major open problems in extremal combinatorics. So let me just write very briefly. So if H is, well, I should define another term. Sorry about that. So there's another term called weakly norming. H is weakly norming if this is a norm. So instead of taking the absolute value outside of the integral, I can take the absolute value inside the integral, like we do for LP norms. Okay. Yeah. So if that's a norm, then yeah, then I say H is weakly norming. And Hatami observed that this is a weaker property. So every norming graph is real norming graph. Let me just distinguish for now. Real norming graph is weakly norming. And another trivial remark is that every complex norming graph is again real norming, because it's a norm on the larger space, larger vector space, the complex valued functions. So it also defines a norm on the smaller subspace, which is real valued functions. So it's if H is complex norming and then real norming. Okay, so if you feel a little dubious about what I've just said, then yeah, as you see here, if f is a real valued function, then the conjugate doesn't really matter. Yeah. Sorry? Yeah. But if f is real valued, then the coloring doesn't matter. It always gives you the same term. Yeah, so and the same term is exactly this one over here. Yeah, so if H is complex norming, then it's in particular real norming. So here's my main result. Okay, so I forgot to. So getting back to here, where I stopped. Yeah, if H is weak norming, which is the weakest property amongst those I introduced, then it satisfies Theorem's conjecture. So, yeah, Theorem's conjecture. I'm not going to state the Theorem's conjecture here. Well, I can spend like 10-15 minutes for this, but the goal of this talk, one of the goals of this talk is to convince you that even without explaining this, this class of graph is an interesting one. Really, you will see in a minute. So it must be bipartite. So because of this, I mean it's a bit of overkill, but H is weakly norming and it satisfies Theorem's conjecture and hence is bipartite. Yeah, it's a bit overkill, but still, yeah. So yeah, that's a very good point. So I'm going to talk about bipartite graphs throughout this talk. Yeah. Okay, so here's a theorem by myself and Sasha. So H is real norming if and only if it's complex norming. So we don't have to worry about the underlying field. Yeah, so we basically prove the converse. Okay, this is nice, but why is this interesting? So, yeah, firstly, even with some very specific example of a real norming graph, it is not so easy to construct coloring, a two-edge coloring alpha that gives you a complex norming color graph. Okay, so let me just give you some more examples. So you've just seen one example here, full cycle. And for any even cycles, you can do the same. For example, you can basically take another alternating coloring like this, and then that gives you the unique up to isomorphism coloring that makes my H complex norming. And there are other examples. What if I take, so this is an octahedron, and if I take the one subdivision of octahedron, yeah, I should be careful. So Yeah. Okay. Yeah, this is the one subdivision of octahedron. I mean, I replace each edge by a path of length 2 in the octahedron. Okay, this is norming. So this is norming by a theorem which I will mention by myself with David. This is norming. But the corresponding coloring for a complex norming property is quite complex. Yeah. So it looks like yeah.
So norming, you mean C norming?
Yeah, the complex norming. So I'm gonna show you which coloring. Okay. Yeah, I'm also confused, which means it's complicated. Yeah, so basically every 6 cycle is colored in this alternating way. Yeah. Like this. Yes. Mm-hmm.
So your theorem like
Sorry? So that's the point. So this theorem is interesting because we don't construct any coloring. Yeah. So as you see, this is complicated, but we do prove that there exists such a coloring. Yeah, without constructions, and the coloring must be unique up to isomorphism.
there is unique coloring alpha.
Yeah, yes.
To make to witness R norming to C norming.
Yes, yeah.
There's no one. But if you
No.
change 0 to 1 and 1 to 0, then it's
Yeah, it's isomorphic.
I wouldn't call it isomorphic. so what's the definition of isomorphic? So we should define isomorphic.
Yeah, we should define the isomorphic colorings. Yeah, in a natural way. Yeah. yeah. So I'm going to talk about the coloring symmetry as well later on. Okay. So yeah, it's it looks interesting because it's not really obvious to construct such colorings. And second, it has some deep message to graph symmetries. So here's a recent theorem by Sasha, which is probably half a year old. Yeah, but I think it's already published. Okay, his theorem states that any weakly norming graph H is edge transitive. So we are really dealing with very symmetric class of graphs. Okay, let me just rephrase this result in terms of group theory a little bit. This means that, so let me just define what G1, G2, G graph means, where G1, G2 are groups that are subgroups of my group G. So these are all groups, and these are subgroups. Possibly non-abelian, not necessarily abelian. Yeah, so it's just general group. Yeah, so G1, G2, G graph is defined by just, it's a bipartite graph. So you just put all the cosets of your G1 here, and all the cosets of G2 here as a vertex. And then you put an edge if they intersect. In other words, they come from the same G. Okay? Yes, so every edge-transitive bipartite graph can be represented in such a way, because you take the automorphism group, you take your automorphism group G of your graph H, and then you take G1 and G2 be the stabilizer of your vertex on each side. And then this G1, G2, G graph is an edge-transitive graph, and that is isomorphic to your original graph. Okay, so here's a fact. H is edge-transitive if and only if it's represented by a G1, G2, G graph. Okay, so we observe something, and here's a conjecture by David Conlon. His conjecture states that, well, I can put my name like very small here, but yeah, yeah, but let me just cite it like this. So here's the conjecture. So he conjectured that a graph H is weakly norming if and only if we have a special choice for G1, G2, and G. Okay, here G is a finite reflection group. And G1 and G2 are parabolic subgroups, no matter what that means. Yeah, so let me just give you a long story short. So parabolic so in finite reflection groups, we have full classification, okay? And there are standard generators of finite reflection group, which we call simple reflections. When you think about geometry, these are just some bunch of hyperplanes that represent reflections. And if we collect them in a nice way, which means their angle is kind of small. So for example, for this one, I take this reflection, and this reflection, and it generates the whole reflection group. Okay? And if I take the subset of these simple reflections, then it generates a special subgroup that is called parabolic subgroup. So it's called parabolic because of some higher geometric reasons. Okay, this is long story short. And yeah, his conjecture states that if H is weak norming, which is an analytic property on the vector space of functions, and then this corresponds to some algebraic property about the group itself, the automorphism group itself. Okay, and we proved actually one direction here, and this is why we conjectured so. So this is theorem by myself with David. Yeah, and furthermore, there's a corresponding statement for norming graphs. H is so real normings. Well, I can ignore this field because of this theorem, but let me just be precise. So if and only if, furthermore, so this whole property plus G1 and G2 only have trivial intersection. So, which is the identity. Okay, and we also proved this direction too. This is also by myself with David in the same paper. Yeah, so this is kind of the ultimate goal of all of these, these things. And if true, then it gives really the answer for the Lovaas question here. Yeah, but this is still open. But the thing is, our theorem here gives some non-trivial positive evidence for the conjecture. So if all of these conditions are satisfied, then we say that my graph is a stable reflection graph. So these graphs, these G1, G2, G graphs with these conditions are called stable reflection graphs. And what we observed in the same paper, so here's a fact. Any stable reflection graph are complex norming. Because of this condition over here, there's a very natural way of coloring, given alternating coloring, generalizing all of these for these graphs. So we just by an algebraic property, there's a very natural way using parity issues to give a coloring. So yeah, this is one, and hence our theorem can be understood as a positive evidence for the conjecture. And there's another interesting conjecture, which is positive graph conjecture. Let me just call it PGC. This conjecture states that if my H density for a not necessarily non-negative valued, but in general real valued symmetric functions F, then if and only if my H looks like this. So here are two parts. So here's, okay, so this is a shape, which means, so here I have an independent set, which is a vertex cut. So independent set, that is a vertex cut. If I delete this, then these two bunches are disconnected. Vertex cut. And there is an involution that while fixing this set, mapping left to right. So the graph looks like a mirror symmetry. So it's easy to prove that this direction is true, but the converse is open. Okay, and
Do you assume that F is symmetric, or do you have?
yeah, symmetric. Yeah. Because here H is not necessarily bipartite. Yeah. So for example, this graph satisfies the conjecture. Yeah. So it's much safer to assume it's symmetric. Okay. So here's another conjecture, and here's our theorem about the coloring symmetry. So this is theorem again by myself with Sasha, and as a generalization of Sasha's theorem here, we prove that if this is complex norming, then alpha must be transitive. So by transitive, I mean, firstly, it is not monochromatic for technical reasons, which you will see in a minute. So secondly, if there are two edges, E1 and E2, with same color, then there exists an automorphism phi that sends E1 to E2. And moreover, if they have different colors, then there exists an automorphism that sends E1 to E2 while color preserving. So it preserves all the colors. So it maps the zero assigned edges to zero assigned edges, and so on. Okay, and here there exists an automorphism phi that sends E1 to E2 while color reversing. Yeah, so it's a strong symmetry for the coloring. And what this tells us is that given this alpha, what we know is there exists an automorphism of H by using this fact. There exists an automorphism H where each orbit is of even length because it's color reversing. Yeah, so it sends 0 to 1, 1 to 0, so each orbit must be of even length. Yeah, so it can be understood as a positive evidence for positive graph conjecture for norming graphs. So one important question here, which was mentioned in this paper, is what about norming graphs? Yeah. So norming graphs are known to have this property actually. So whenever you take any function f, so in fact you don't really have to take the absolute value here. And then it's a very nice question to ask if in a norming graph, is there such an involution? Yeah, and we don't prove that, but we give some weak positive evidence for that, where there is an automorphism that has even length orbits for, so every orbit is of even length.
I think I don't understand the statement of that theorem correctly. So you say whenever H alpha is C norming, alpha will be non-monochromatic, because you also said that the alpha doesn't matter if we are R norming. So we could take a monochromatic alpha, so this cannot be true.
I mean, to be complex norming in a full sense, I mean, without alpha, without considering, I mean, taking any alpha works for real valued f.
Yes.
But to get the full norm for the space of complex valued functions, we need special alpha. Yeah. Yeah, and there are. Are you happy with? Here? Yes, so if these two edges have different colors according to alpha, then there exists an automorphism in H that sends E1 to E2 while reversing all the colors. Yeah, so 0 becomes 1, 1 becomes 0. Yeah. Yeah. Okay, these are the results. And yeah, so it tells us something about graph symmetry, which looks nice. And the third reason is applications to some open problems. So here are some applications. So Hamed Hatami, in his pioneering work on these graph norms, he asked several questions. How much time do I have? 20 minutes? Yeah. And one of them, so the first one being, so let me just list up some questions to just, so there are several questions. The first question is the hypergraph generalizations. This remains open. Well, it remains open for the graph case, then there's no kind of chance that we can nail down all the hypergraphs. So hypergraph generalizations, but this has been studied by Hamed himself, and also in the paper by myself with David. So yeah, it's somehow studied at least. And the second question is, so the order is not so important, but the second question is there an edge-transitive graph that is not norming, not weakly norming? So this is the second question, and this has been answered by Kroll, Martins, Pach-Rockner. Yeah, so H-transitive bipartite graph H. Yeah, that is not weak norming. Yeah. So they constructed, there exists an H-transitive bipartite graph that is not weak norming. Yeah, so. Yeah, these people constructed. The question is so this is solved. So so these are all solved. Yeah, so this has been studied, and this has been settled. Yeah, it's answered. Yeah, answered. Okay. Okay, this is answered. And the third question and the fifth one are some specific examples that he was interested in. The K5 phi minus C10, which is so far the smallest case where Fedorenko's conjecture remains open. He asked, this is weakly norming. And as a generalization of his cube theorem, which means he proved that every hypercube is weakly norming. So he asked this graph, which looks like cube, but let me just, so it's a 6-cycle, a pillar of 6-cycle, which looks like a cube, but yeah. So this one?
What is 3 and Q? What is Q3?
3. This is Q3 and this is Q5. So in his paper, and both are answered. Yes. Yeah. Yeah. So these are not weakly norming. Yeah. Yeah. So these are not weakly norming. That's that's by myself with a Hamburger student, Björn Schurke. Yeah, and
this is not weakly norming. Answer towards Q2.
I think this is not edge transitive. Right. Yeah. So Theorenko's theorem solved this question too. Yeah, it's not edge transitive because if you draw it like this, then this edge is not not transitive to this one. Yeah. Okay. And the fourth question I didn't write is the hypercubes are norming or not.
It's weakly norming.
Yeah, it's weakly norming by the theorem. So this is weakly norming by theorem of Hatami. This is one of the main results in his pioneering work. And we answer this question by an application of this result. Yeah. So we in fact proved that. So this question was about real norming, but these are the same. But we proved that this is not complex norming, and hence is not real norming. So this is a beautiful indirect way to answer this question, right? Yeah, and other questions like the sixth question, the sixth one is the last, and some Banach space geometry questions. I have space geometry like uniform convexity and smoothness. And this was also answered by Frederick Garber, Jan Hladky, and myself. Yeah. So overall, except this wide open question, which is harder than the Lovaas question, we basically settled all the questions appeared in the paper.
You mean paper by Hattani?
Yeah, the paper by Hattani.
Also answers Q2, right?
Yeah. So D must be larger than 2. So yeah, Q2 is isomorphic to the full cycle, the two-dimensional cube. Yeah. So okay.
Yeah, Q4
Yeah. Q must be S-transitive.
Q4 is not.
So it was about weak
weekly
norming.
norming.
Yeah. It was about weak norming.
So Q4 means hypercube is weakly norming for this non-norming.
Yes. Yeah, and it's in general quite interesting to distinguish between this norming property and weak norming property for various examples. For example, in the paper by myself with Bjarne, we proved that this guy, KTT minus a perfect matching, is not norming. And this graph in particular was shown to be weakly norming by Lovaas. Yeah. Yeah. Mm-hmm. Yeah, and furthermore, so this one is this one takes different approach. So this one's with Bjarne Schulke. So this one takes different approach, and in this paper. Yeah. Okay, and we also proved that, for example, the one subdivision of complete graph KT for t greater than 3, because when t is 3, the one subdivision of triangle is a 6 cycle, is not norming. But it's weakly norming by myself with David. Okay, if time allows, then let me show you why, how we obtain such an application very briefly. Again, long story short, so the theorem is the one subdivision of KT is not norming. So we proved that this is not complex norming. And here's an interesting fact. Whenever you have a symmetric enough 2H coloring of your one subdivision of KT, then it gives you a tournament. So basically, so the one subdivision of complete graph looks like this, and you color in a alternating, well, not necessarily alternating way, but at least you have something like this. Yeah. Then I can construct a tournament which looks like this. Yeah. So here I have a transitive coloring alpha, and that corresponds to an arc transitive tournament. Well, to be arc transitive, you should have the same degree, same out degree and in degree for every vertex. So it easily proves that you should have your t to be an odd number. Yeah, so it's enough to prove that this is not norming. And well, because I prepared quite a bit, but but let me just give you one exercise for your students for the undergrad graph theory course, say. Yeah, so here's an exercise. So if my T is arc transitive on the odd number of vertices on 2d plus 1 vertices, that was T, right? Vertices, then your D must be odd too. So it again reduces some cases. Yeah, so here I prove that my T is an odd number, and I replace T by 2d plus 1. Then if it's arc transitive, then D must be an odd number. So that's done by counting a directed 3 cycles. Yeah. So for regular tournaments, to be short, for regular tournaments, there's a constant number of the directed 3 cycles in a regular tournament. This is done by counting these guys. So it's either this way or that way. Yeah. So for every triples, you have 2 cases. Yeah. And the contribution. So when counting this, the contribution from these guys is 3 times. Plus n to 3 minus the number of these guys. Because this is the this is the case when your triple doesn't induce directed 3 cycle. Yeah. Unlabeled. Yeah. So, and then you can compute, this is a fixed quantity because every vertex has the same even degree and the out degree and in degree. So you can just nail down the number of directed 3 cycles in your regular tournament. Yeah. And then if your tournament is arc transitive, then you can divide it out by the number of arcs because every arc must extend to the same number of directed 3 cycles because it's transitive because of the symmetry. And that gives you this fact, D must be odd. Yeah, and that gives you further reduction. Yeah, so this is a baby case. Yeah, and we analyze further to nail this theorem down. Yeah, so by using this symmetry of colors, there are lots of different methods to attack these kinds of problems because we get an extra symmetry inside the graph. So let me just finish by talking about some open problems. So, well, the ultimate goal is to prove this ultimate conjecture over here, the complete classification of weakly norming graphs or norming graphs. But there are some other interesting questions. For example, distinguish norming graphs versus weakly norming graphs for reflection graphs. So here we have variety of examples that are weakly norming. So it should be interesting. So these graphs, for example, this graph, or the hypercube, these are all graphs in this class. So which we call reflection graphs. This is an interesting question to generalize all these theorems. And second, let me just mention an interesting question that connects to positive graph conjecture, which I just erased. Yeah, so is there an involution? So involution on the norming graph H. So by involution, I mean the following. So you just split your edge set into 2 pieces and just maps one to the other. So no edge is fixed. Every edge can be paired up to some other edge. So this is not enough to settle this positive graph conjecture for norming graphs, because it really does need this special vertex cut, which is a fixed set according to this automorphism. But this is a weaker but still interesting question, and it also connects to a conjecture called polycirculant conjecture. Sounds cool, right? So this is a conjecture in 80s, which has been conjectured a couple of times, and hence being a little bit folklore, and it remains open. So this conjecture states that any vertex transitive graph H has an automorphism of special type, which has the same length for all the orbits. So all orbits are of the same length. Well, if I take identity, then it's too trivial, so non-identity automorphism. Yeah, so non-identity automorphism where the orbits are of the same length. Yeah, and yeah, this is reminiscent of this conjecture because involution, for example, the involution I explained is basically, so if this is true, then it confirms this polycirculant conjecture for the line graphs of norming graphs. Yeah. So yeah, this is it for today, and thanks for coming.
All right, any questions?
You know, weakly norming bipartite graph specify Theorem property or
Yeah, Theorem-Coase conjecture. Yeah.
How about H20?
You mean
Just H20.
H?
That is known about Theorem-Coase property.
Ah, okay. So you mean if Theorem-Coase conjecture is true for edge-transitive graphs? Probably nothing. Yeah, probably nothing. So there's a theorem by Balash-Segedi saying you may assume G is edge-transitive, the target graph G here. Yeah, but that's it for yeah.
Other people can.
Other questions?
So in the Coulom's conjecture,
Mhm.
say that H's are not only the condition with the intersection of geometry discrete, but is there any special reason why you want H to have the trivial intersection? We can the sufficient condition to
Yeah, there's a good reason for this, but again, it needs some time. But again, long story short, what we do in this paper is basically algebraize the applications of Cauchy-Schwarz inequality. Yeah, and then to apply Cauchy-Schwarz, we need positivity of corresponding functions if the symmetry, the graph symmetry we apply Cauchy-Schwarz has an edge in the cut. So this is more or less technical looking reason. But you might think that this is nothing but some technicality, but I do believe that it has some fundamental reason. Yeah, it connects to the positive graph conjecture and all these extensions like these graphs are the complex norming graphs and so on. Yeah, so to get these the conjugate assignment, the coloring for these guys, this is also necessary. Yeah.
So all these properties like norming and weakly norming occurs when graph is highly symmetric.
Yes.
And those graphs must have some kind of like properties on eigenvalues or something.
Yeah,
are there some studies relating these spectral?
Yeah. For example, if you take your H to be an even cycle, then it corresponds to the 2K norms of your spectrum. Yeah. So by taking this diagonalization of your matrix. Yeah. So you can think of this G as a matrix, the adjacency matrix, which is symmetric. Yeah, and then the 6 cycle count, for example, is the sum of 6 power
of the eigenvalues. Yeah. So it corresponds. So the easiest proof, for even cycles being norming is to take that way. Yeah, but I don't know for other graphs. So yeah, if they are represented by some polynomial in terms of spectrum. Yeah, I guess not. I thought about this for a while, but yeah, all of my colleagues were kind of pessimistic.
Alright, any other questions?
Is there a example satisfying the pseudo-Renko property but not weakly norming?
Yes. There are many actually. Yeah.
Yeah. So as you see here, these are very symmetric class of graphs. Yeah. So in particular, any weakly norming graph has the same degree on the same side of the bipartition. Yeah, and there are many such graphs that satisfies Zelenko's conjecture, but the degree is very irregular. Like if you take one vertex that's adjacent to all the others on the other side, then it must be Zelenko by theorem of Kononov-Sudakov. Yeah, so in that sense, unless your graph is a complete bipartite graph, yeah, it's not weakly norming.
Of logos. So answer is not in general. It's not norming.
Yes.
In
Yeah.
So property 3, the third property, triangle inequality, is the most important.
Yeah.
And then can you say weak triangle inequality, something like we can multiply some constant less than 1 in left hand side. Is there a universal constant C, let's say delta rather than C, delta, non-negative, positive delta, so that it's weakly triangle inequality.
I suspect I should check, but my like 1 second instinct is one can remove such a constant by taking the tensor powers.
Tensor product.
Yeah.
Because 1 over EH, so you can make it.
Yeah.
Then we can normalize it in a sense.
Yeah.
Because we avoid that kind of trivial case. So it can be depend on number of edges or number of vertices, and so then it's universal constant delta, so that something like it's a universal constant with respect to when number of edges is fixed as a function of number of edges. It's not constant then. Anyway, so I can think of something like that. Because if there is normalization, we can normalize the constant. Anyway, so the reason I'm asking is that property may help to prove Theorenko's conjecture. Maybe, may not.
Yeah, there's an interesting connection from this guy to Zelenko's conjecture, which is so-called step Zelenko property, which uses this triangle inequality. Basically means, like apply this
Semiradis regularity lemma, yeah, then the model graph you are considering is this random graph across the partition. Yeah, so the step Sidorenko property is roughly means so whenever your graph is partitioned in some way, yeah, and suppose you average the edge density across the partition, then your edge density decreases. Yeah, so for example, if you take a trivial partition, then it gives you the edge density, so it means it's Sidorenko. Yeah, so it's actually, such a property is equivalent to Wick-Norring property. So it's, yeah, the one direction is given by this triangle inequality, and the converse is proved by Jan Plotky and his colleagues. Yeah, 5 of them. Yeah.
My last question is,
Any progress about K5 minus 6?
On this Sidorenko connector, unfortunately not.
If you don't count this as a progress, then yeah. But
Related to Sidorenko.
Yes.
Definitely progress.
Yeah.
Not that direction.
Yeah. No, nothing.
yeah.
Right. No more questions? This is the last question. It's my last. Okay. Let's thank the speaker again.